Functional materials possess a combination of specific tunable properties that ensure their exploitation for a wide range of real-world applications. Ductile and tough tungsten-iron-nickel composite, fabricated by vacuum diffusion bonding, is a solid material of choice for fusion reactors, while electrodeposited nickel-iron-tungsten alloy has excellent magnetic and electric properties and used to fabricate microtransformers. Furthermore, iron-tungsten alloys have shown their excellent biocompatibility and biodegradability that pushed the idea to fabricate porous iron-iron-tungsten scaffold for future application in bond tissue engineering. And also, biocompatible iron-tungsten nanotubes having tunable magnetic properties were electrodeposited for sensors fabrication. Therefore, iron-tungsten is a functional material that can change its properties dependently on the preparation conditions and used for all scale applications, from micro to nano. Here at Vilnius University in Lithuania, we are working on green electrochemical synthesis of iron-tungsten alloys for target application, while avoid the use of critical raw materials and hazardous chemicals in the electrolytic bath, minimize waste and maximize the economic viability of the process. The overall distribution of metal species in electrolyte is pH dependent and also is a function of other species in the bath. The modeling of such distribution is based on the equation set including equilibrium constants for all compounds dissociated or formed in solution, the mass balance equation for all forms in the equilibrium mixture, and the charge balance equation. Most of iron-containing plating baths operate with iron 2 salts as a source of iron. However, fast oxidation of bivalent iron ions to iron 3 eventually reduces the bath lifetime and reproducibility of the results, as the bath composition is not constant with time. Complexing agents can inhibit this process but not prevent it. The development of iron 3-based plating bath consists in the selection of suitable complexing agent able to prevent formation of sparingly soluble iron hydroxides. As ammonia is volatile, we have focused on glycolic acid, and the stability of new bath was estimated based on the theoretical simulation of complexes distribution. The use of both citric and glycolic acid stabilizes the electrolyte, as the concentration of 3 iron 3 ions does not exceed the one required to form hydroxide precipitate. Due to the complexes distribution, the composition of deposits is very sensitive to solution pH. Thus, tungsten-rich alloys are deposited up to pH 7, while 99% of tungsten is present in form of complex with glycolic acid. According to literature, tungsten glycolate complex is the molecule with small volume, which can move faster to the cathode and discharge easily, compared to citrate complex molecules. That increases the current efficiency of iron-tungsten deposition process up to 70%, compared to maximum 50% reported for citrate ammonia electrolytes. As the concentration of glycolate complexes decreases, the deposition of iron-rich alloys occurs and the current efficiency drops. By changing the deposition conditions, alloys with various tungsten content from few atomic percent to 25% of tungsten can be produced. Iron-rich alloys are characterized by rough and porous morphology, while the increase in tungsten content leads to remarkable disappearance of pores and substantial surface refining. Apparently, the structure of deposits changes from nanocrystalline, characteristic for alloys with low tungsten content, to amorphous one, characteristic for alloys rich in tungsten. The mass biospectroscopy has shown the presence of alpha iron phase mixture with tungsten solid solution in iron below the tungsten solubility limit at 14 atomic percent. With further increase in tungsten content, intermetallic compound iron 2 tungsten and iron solid solution in tungsten are formed. The structural changes eventually influence on the properties. In this way, the hardness of electrodeposited iron-tungsten alloys increases with tungsten content, reaching approximately 10 GPa for alloy having 25 atomic percent of tungsten, which is comparable to the hardness of electrodeposited chromium tested at the same conditions. At the same time, the alloys rich in tungsten have low saturation magnetization and show soft magnetic character, what makes them appealing alternative materials for design of bioMEMS, which nowadays are mainly based on nickel compounds. More information about the electrochemical design of iron-tungsten alloys find in published articles.